I request all the participants, please go through the PDF file which I have shared on the WhatsApp group of NGP 2026 Bootcamp. Please refer to the PDF file which I have shared with on WhatsApp group.
हा सर, सुरू करा तुम्ही. चालू झालेलं आहे.
Okay. So good evening all. So I welcome all the students, all the participants, NGP aspirant students, once again our NGP Bootcamp series. So we have covered almost 4 sessions on a different topics of the physics. And yesterday we had a quantum mechanics, which was conducted by the Professor Dr. G.H. Gotesa. And as we are celebrating this year is a quantum mechanics and quantum computing year, celebration of quantum century of quantum mechanics and quantum computing year. So today we are going to have a session on the electrodynamics, which is another core subject in physics. So amongst us, we have Professor Sanket Gupta sir. Sanket Gupta sir is an assistant professor in Progressive Education Society, Modern College of Arts, Science and Commerce, Shivaji Nagar, Pune. Sir is pursuing right now a PhD on the variational quantum algorithms, and sir has experience of teaching for the UG and PG level almost 15 years, and sir has uh, taken the core subjects like the statistical mechanics, electrodynamics, quantum mechanics, mathematical methods in physics, classical mechanics, core subjects of the physics in UG and PG level. Also, I'm happy to say that Sir was a state-wise top 1% candidate registered in Maharashtra, India for the NGP exam. So I must say, Sir is the right person to have a today's lecture. So as I said, Sir was top 1% in a state for the NGP 203 and 204. Uh, so I welcome Professor Gupta sir to deliver today's session, and sir is going to focus on the electrodynamics. So thank you very much, sir, for accepting our invitation. So over to you, sir.
Thank you, Shinde sir. Am I audible?
Yes, sir, you are clear.
Thank you for welcome as well as the introduction that you have given for me. I also thank IAPT organizers of this bootcamp for inviting me here and having me here. I also like to thank all the enthusiastic physicists who are here to take the first step and learn the trade. I am thanking the new enthusiastic physicist in advance because I'm hoping to have a session which is interactive. So I'm expecting that all of you participate. So what we are going to do is we are going to solve some problems, and I'm expecting, and as I said, that we in my sentence is with double quote because I'm expecting that you also contribute towards the solution as we solve the problem. So I'm hoping that it is not a monologue, but you also participate. Um, Before we start with the actual problem. Let me tell you how we are going to proceed. I have shared with you a problem set, or rather, thanks to Shinde sir, through him, I have shared the problem set, which I will also show to you on the screen once I switch to the other device, where I can write on the screen and where I'm going to solve the problem. But before we start doing it, I want to give an analogy of solving a physics problem with opening a knot on a rope. So if we have a knot on a rope and we want to solve it, it is very we want to open that knot. It is very similar to solving the problems in the following way. The steps that we take to solve the problem is very similar that the step we take to open the knot. It goes like this. The first step is to observe the knot very carefully, how it is structured, what are superficial sections of the thread that you can see on the knot, and what are the hidden sections that you cannot see, some tricky points. which are there on the knot, and then there are some sections which are underlying the above layer and which are not observable superficially. You have to assume, or you have to anticipate that these sections are going to be there. It is with problem solving, I think it is very similar to that. The first step in solving a problem is to read it very carefully. You have to identify what are the physical quantities which are given. You have to identify the quantities which are not given and which are unknowns, which we want to figure out as we solve the problem, at least when the problems are from UG or PG level. Generally, these are the steps. The next step in the analogy that we are considering in opening the knot is, then you have to identify a couple of sections or ends of the knot which you have to pull so that you can loosen the knot and ultimately open the knot completely. So you need at most 2 to 3 sections which need to be pulled. Just like that, in physics problems, we have a similar thing. We need to identify 2 or 3 concepts in physics which are going to help us solve that particular problem. So this is the next step that we take when we solve the problem as we open the knot. And the next step in opening the knot now is to apply the skills. You hold the knot with some tool, or you hold it with your finger, or you hold it with fingers of your friend because she has grown the nails, and then you apply appropriate amount of force to loosen the knot and ultimately open it. The same thing that we do in physics, that we then use, once we have the concepts, then we write down the equations. Then we use some mathematical jugglery, use some mathematical tricks, tools, such as solving quadratic equations or taking trigonometrical identities or something like this, and write a relation where the unknown quantity is on the left hand side of the equation and all the known quantities are as a relation written on the right hand side, so that we can plug in the numbers and figure out what is the answer to the problem. So these are the 3 steps that we take as we open the knot and as we solve the problem. So what we are going to do is, in the end of each of the problem, though we are not going to articulate it, we won't mention it in perfect words, what is the second step, which are the key concepts which we need to solve, and then third steps, the skills that are required to solve the problem. So what I'm saying is this: the second step is to identify the key steps, key concepts of physics, which are normally 2 to 3 at UG level problems. And the third step is to identify the skills that you require, which are definitely more than the number of key concepts that you use, and then which we use to solve the problem. So after we solve each problem, and in fact, I'm expecting all of you to speak in between as we solve the problem. But at the end, I want exclusively you to identify the 2 or 3 concepts that we use to solve the problem, and then the key, uh, the skills that are required to solve the problem. Am I making myself clear? Am I making any sense? Anyone from the participants?
Yes, sir.
Please answer the questions. Yes.
Yes. So the last step, identifying the key concepts and identifying the skills, is exclusively for you. I'm not going to add anything to that, and that comes after we solve a particular problem. So let's begin with the problem. Give me a minute. I will switch the device and use another device where I can write on the screen. So I'll disconnect from this meeting, and I think yeah, other device is already connected. So give me a minute. I'll switch the devices. Thank you. Can anyone please tell where is the button to disconnect? I can't find it.
Beg your pardon, sir.
I'm not able to find the disconnect button.
Are you using the two devices?
Yes. Okay, I'll simply turn off this PC. That should work. Hello, am I audible?
Yes, sir.
Yeah. I'll start sharing the screen now. I'm not given access to share the screen, is it?
So, you have been made a co-host.
Both his devices.
Just a second. When I
Gurupad ma'am, are you there?
sorry.
I'm just talking to Gurupad ma'am, the host of this
Okay.
session.
Okay.
So she has a right to change the host.
Okay. When I
Just a
try
minute.
to
I'll just talk to ma'am. Just a minute.
okay, okay.
There are two connections, Gopri sir. Second connection is not co-host, the
Sorry, sir.
only participant. Yeah, just a minute. Ma'am will make you co-host.
Yeah, okay, okay. No problem. I'm waiting, sir.
संकेत सर तुमचं कोणतं डिव्हाइस होस्ट करायचं आपल्याला?
आता बहुतेक एकच दिसत असेल
एकच आहे ना? ओके,
अँड्रॉइडचं
ठीक
जे
आहे.
आहे ते.
Just a
हो.
minute.
एकच आहे सिंगल असा
एकच
डिव्हाइस.
मिनिट. आता बघा बरं शेअर करून.
मला अजूनही तोच
नाही,
मेसेज येतोय. ओनली
नाही
द होस्ट
नाही
कॅन
सर.
शेअर.
नाही, मी आता तुम्हाला को-होस्ट केलेलं आहे सध्या.
नाही आईना बांबू त्यांना को-होस्ट केले तुम्ही. ते
नाही, मी
रिमूव्ह करा.
आता ओके. जस्ट अ मिनिट. जस्ट अ मिनिट. कारण की पार्टिसिपंट स्विच होतं कंटिन्युअसली. हा. आता बघा सर.
येस येस हो.
आता होतंय शेअर. यू आर नाउ को-होस्ट.
येस झालेत को-होस्ट.
स्क्रीन विजिबल आहे माझी आता.
Your name is just visible.
नाही,
Your screen is not visible.
Oh, screen is not yet visible. Just a second.
share the screen, sir.
Yeah, when I hit, just a second. Yes, it should be visible now.
Yes, your screen is now visible.
Yes.
Yeah. Participants, shall we start with the first problem then? I will open this notebook and I will solve the problem here. So let's begin with the first problem. I guess everyone has the problem set. Is it the
Yeah.
case?
Yeah.
Yes. So can everyone see the problem? Let's start with the
Yes,
first
sir.
problem. These are
Yes, sir.
problems that I have taken from previous NGPE question papers. This I think is 2022 paper. So we will begin with the first one. As I said, the first step is to read the problem carefully, identify its structure, so that we can identify the sections or the keys concepts from where we have to start solving the problem. So let's read it carefully. I'm reading it out loud here. In a certain region of space, the field is expressed as this equation tells 3xi plus 2yj plus zk, where I cap, j cap, and z cap are the unit vectors. The value of surface integral over the closed surface bounded by this region between x is equal to 0 to 3, y is equal to 0 to 2, and z is equal to minus 1 to 2 is to be figured out. Now this is a problem asked in NGP where the options are given. I have intentionally not considered them. Okay, so let's now begin by first having a look at the concept that we need to use to solve this problem. We need to solve this problem. So can anyone please try to answer this question? What do we need to solve the problem? Or even before that, what we have to do is this. So what we are given is there is some region in space where the electric field is already known. It is given to us. And now we want to find out this surface integration EDS over the closed space. Just a second, I'll be back. Give me a minute. Yeah, I'm sorry. So let's go back to the problem. So we want to find out this surface integration. If we try to follow the method where we use this equation itself to solve the problem, what we have to do is that we have to divide the region of the closed surface into infinitely small subsections. For each section, suppose the area is ds, which is infinitesimally small. And then we write this vector ds, which is such that its direction is pointing outside the surface and it is normal to the surface. So we draw this unit vector which is normal to the surface at that particular point, and then this ds vector becomes magnitude of the area into the unit vector which is, as I said, is pointing directly outside and normal to the surface. Now we know what is the electric field in the region. So we know E as a function of x, y, and z. This is given to us. So we then, for each of the sections, have to multiply this electric field at that point, E, at a given point. Say you start with x1, x2, y1, z1. You multiply that or take a dot product of this electric field with this ds1 unit vector, which is the first vector, first small infinitesimally small section that we have identified, and take this dot product. Now naturally, since this ds is infinitesimally small, this first term is going to be infinitesimally small. But let's not forget that we have to integrate it over the closed surface. So in this way, we have to now go over each and every section and then see what is the electric field there at that point, x2, y2, z2. Take the dot product with this vector ds2, and in this way go on considering all the infinitesimally small but infinitely many sections of area throughout the surface, and then in the end what we get is the last nth, which is tending to where n is now tending to infinity, this term which is a x n y n z n multiplied with dsn, and this integration is this one. When we mathematically do it, we know that xy e is function of xyz at every point. So we have to write ds in the same way and then integrate it, and it's going to be double integration because integration is over area. So we have two variables for surface, because surface is two-dimensional geometrical figure which is embedded in the three-dimensional space. But naturally, as you see from the given information, it is clear that where let me write down what is the electric field there. So electric field is 2, or rather 3x I cap plus 2y j cap plus z k cap. And then we are given the region. The region is such that x ranges from 0 to 3, y ranges from 0 to 2, and z ranges from -1 to 2 plus 2. So, and we want to calculate this integration, surface integration over the closed surface for given electric field and for given region. So it's mathematically very tedious, though not impossible. It is tedious to do it this way, and therefore it is not good idea to take this integration. We use a nice theorem in physics already, and then use it to solve the problem. So can anyone try to guess which concept do we use so that solving these problems becomes easier, much easier? I'm audible, right?
Yes, you're
Yes,
audible.
yeah.
Yeah. Someone from the participant, those who have studied electro. Yes,
Sir,
Anish.
Gauss divergence theorem.
Yeah, we use Gauss's divergence theorem. Can you try to, if you remember, can you tell me the equation?
Sir, divergence of E.
Yes, this surface integration. Instead of writing now v for vector, I will write e for the vector. So this is the quantity that we want to find out, e dot ds, which is the left hand side, and it is now the surface integration. And what is the right hand side here?
A
It is now
divergence of E into volume element.
into volume element. And now since we are integrating over volume, we have three integrals here, where x runs from 0 to 3, y runs from 0 to 2, and z from -1 to +2. So, so this is the equation, which is Gauss's divergence theorem, which is the key concept, as I said, which is going to help us solve this problem. So this left hand side now is the unknown, and we want to find out the right hand side. So we will start by first calculating the divergence of the electric field. Right? Let's start first by writing the del operator. Does anyone know what is this del operator? It is a vector operator, vector differential operator. So what is this operator? Anyone?
Del by del x into
It is
x
partial
component
dou by dou x, partial differentiation with respect to x into I cap. Please continue.
plus the del y into the y component of electric field.
No, here we are simply writing the del operator, the vector operator itself. We are not yet plugging in the electric field. So del operator is basically partial differential operator, and it is a vector operator. So the first term, if you call it so, first operation in that operator is dou by dou x into I cap. So this dou by dou x is partial differentiation with respect to x. Dou by dou y is partial differentiation with respect to y, which is multiplied by j cap, and therefore it makes this term then becomes a vector operator. And the last term is partial differentiation with respect to z into k cap, where k cap is the unit vector along z axis. So this is the del operator. And we now operate it onto the electric field which is given to us. Electric field given is 3x I cap plus 2y j cap plus z k cap. So when we operate it, It's basically the dot product. Divergence is a dot product. So we take dot product between this operator, and this is now a dot product here. And just like in dot product, what we do is we multiply the x components, y components, and z components and add these three terms together. That is what we are going to do. Except now this is an operator. The first term is operator, and this term is operation. So we dou by dou x onto this electric field. Now I dot I is equal to 1, and it's a scalar quantity. And therefore the first term here becomes dou by dou x, and that operates onto 3x, and I dot I is equal to 1. Then we operate the first term on the second term of electric field. Here what we get is partial differentiation of x with y component, but we have I dot j cap, which is equal to 0. And therefore this cross multiplication, it doesn't give us any non-zero term. So we don't have to worry about it. Finally, this term here, when we operate dou by dou x onto z component of electric field. Again, in that operation, we also have I dot k cap, which also is 0 because the dot product is equal to 0, and that term also does not contribute. So this is the first term that we get. Second term now is operation of this onto electric field. This is a vector. So again, only one of the three terms will survive. J dot I cap is 0, J dot J cap is equal to 1, and that term now survives. So what we have is dou by dou y into 2y. The last term is dou by dou z into z, because k dot k is equal to 1, a scalar 1, and rest of the term will vanish when I consider this operation with of the z component of del operator with rest of the electric field. Is everyone with me this far? Is it fine?
Yes, sir.
Yeah. So now let's complete it. What is partial differentiation of 3x with respect to x? All you need to do is, if there is, you differentiate it with respect to x. So even if there are other variables, you treat them as constant. In this case, that is not the situation with any of the terms. So what is partial differentiation of 3x with respect to x?
3.
3. For second term, partial differentiation of 2y with respect to y is
2.
2. And the last term is
1.
1. And therefore, del dot E is 6. So in this equation, this is the equation that we are going to use to solve the problem. We have figured out what is del dot E term here. Am I right? Is it fine?
Yes, sir.
And let me ask you a question now. Because del dot E turns out to be equal to 6, we are lucky here. What we want to find is this. Let me again write it. We want to find del dot E, and then we want to integrate it over the region from x is equal to 0 to 2, y is equal to 0 to, sorry, x is 0 to 3, y is 0 to 2, and z is equal to -1 to 2. And this is going to give us the answer. I will not write the complete surface integral term here. And we have this at 6. And I'm saying we are lucky in this case because we got simple 6. What can be the reason behind that? Why am I saying that having del dot E at 6 makes our life much easier as we solve this problem?
Sir, we can take it outside. Otherwise, we can have variable and
Yes, exactly. Thank you. So what we have is del dot E is 6. So it's a constant. It's not a function. And therefore, while integration, as she said correctly, we can take it outside the integration sign. And what is left is this integration x is equal to 0 to 3, y from 0 to 2, and z from -1 to 2 into integration this volume element dv, where dv now I can write as dx. I won't write the limit. Let me be a little lazy here. And this dv can be written as dx into dy into dz. Volume, small volume in element is going to be this product. And now I can integrate it separately. Integration of dx, or this, if I don't skip a step, what I get is this integration of dx from 0 to 3, integration dy from 0 to 2, and integration dz from -1 to 2. So therefore, what I get is 6 into integration of dx is x, limits are 0 to 3, into integration of dy is y, so I get 6y. Okay, let's keep it this 6. We'll take it as common. So let me draw this cursive bracket, and the limits are 0 to 2, plus for z integration, dz integration is z, and limits are now 2 to -1, and all of this is multiplied by 6. So therefore, the next, what we get next is, when I plug in the limit for this first term, I get 3 minus 0. So 3 into, for this, I get 2 minus 0, which is equal to 2, into, for this last term, when I plug in the limits for z, I get 2 minus -1, and therefore it becomes 3. And all of that is multiplied by 6. So when we solve this, when we find the product, we get our answer. And can someone please tell me what is it? Oh, what am I doing? This is plus. I'm sorry, someone. This is not into, this is plus. Yeah.
No, sir. No, sir. No, sir. No, sir.
No,
This is
sir,
correct.
it should be
It was
multiplication.
3 into 2 into 3. That will be 18 into 6.
Oh no.
So answer is 108.
Yeah.
Correct.
Yeah.
Hmm.
Yes. So the answer turns out to be equal to 108, which is one of the option in the question paper. You can verify that. So this is the first problem. Any doubts here in this problem? I'll zoom out so that you can see the whole screen, at least part of it. Any questions? If no, then we have the task which you have to complete. If there are no questions, no doubts, what we have to do next is to identify the key concepts that we used to solve the problem. So what are the key concepts that we required?
I think it is
Someone,
easier to solve a volume integral as compared to surface integral, so we can convert uh, surface
that
integral
is
to
right. And how have we achieved it? What you said is exactly correct. But how have we achieved it? By
by
using
Gauss divergence theorem.
Gauss's
Differential
divergence theorem.
formula.
Right? So this is the key concept. Anyone else thinks that we need something? Is there any other key concept as we need to solve it? And then rest are skills, of course, there. But before that, if anyone thinks that we need something more, a concept without which we can't solve it,
No,
no.
that's enough.
So what are the skills required then?
Integration.
You need to calculate first.
Double
You need to know how to find out the divergence. Any question? Any doubt? I heard someone was saying something, I guess.
No, sir. Continue. Please continue.
Yeah. Okay. So what are the skills that we used? First, first you need to know how to calculate divergence of a vector, without which we cannot solve the problem. What else do you require? Finding the volume integration. So let me write calculating volume integration. I said that I'm not going to do it anyway. Doesn't matter. Calculating volume integration, and then plugging in the limit and everything comes in this second skill itself. And what is the third skill that we require here? Some basic algebra. That's all. You can't, the foolishness I did, you cannot add instead of multiplying. Thank you, sir, for correcting me. So basic algebra, right? With this, the whole problems can be solved. Is it fine? Any questions in here?
No,
Shall
sir.
we go to the next problem then?
Yes, sir.
Yeah. So let me switch the screen. So this is, let's read the problem. This is now problem number 2 in the problems that in this problem set that I have shared with you. Let's read it carefully. I will read it out loud. In a simple circuit for charging of capacitor of 100 microfarad through a resistance of 10 kilo ohm in a series by a battery of 6 volts in your laboratory, the displacement current ID between the capacitor plates after 500 milliseconds shall be. So, let's, if you have studied this, you know that RC circuit in series is something like this. What we have is a battery, then we have a capacitor. I will simply draw a parallel plate capacitor, and I'm intentionally drawing it. Let's first, just a second. So this is the parallel plate capacitor. Then a resistor R is connected in series. And for this particular problem, we are told that this battery is of 6 volt, capacitor is of 100 microfarad, and resistor is 10 kilo ohm resistor. So this is the circuit. And we want to find out displacement current ID at t is equal to 500 milliseconds. So, where do I start? Or can someone please chip in and tell me what displacement current is?
Sir, we consider that there is because current can flow in a closed loop, so we consider there is a current between capacitor plates that is known as displacement current.
Yes, right. So this is very interesting for displacement current. If you have, or you must have studied Maxwell's equations. Maxwell's equations are basically four equations, four laws which were already there when Maxwell came, and he did maths and told that with these four laws you can say that light is electromagnetic wave. So the first is Gauss's law, which existed at that time. Second was the law that magnetic monopoles don't exist. Then third law was Faraday's law of induction, and fourth was the Ampere's law. So this displacement current term is actually something which missed in Ampere's law, and Maxwell added that term for ID. And for those who have not yet studied it, if you are in first year or second year of your BSc, you may not be familiar with this displacement current. Let's quickly see what displacement current is. Suppose initially to this circuit, let me add a key. So what we have is a key here, and initially at t is equal to 0, the key is open. This capacitor is completely discharged, so there is no charge on the plates of the capacitor. At t is equal to 0, we close this key and the circuit is complete. And what will happen is uh, the, the, the capacitor will start changing. But as I say, the circuit is closed. Am I being completely correct here? Is the circuit closed in this case even after the key is closed? Yes or no? I'll repeat the question. At t is equal to 0, I close the key. Can I say the circuit is complete in perfect sense?
Sir, there is a gap between capacitor plates.
Yes. And because of that, these 2 points, two plates of the capacitor are not connected by using any conductor, and therefore this actually is an open circuit still. But what will happen is this plate, let me call this as plate number 1 and this plate number 2. So plate number 1 is connected to positive terminal of battery, and plate number 2 is connected to the negative terminal of battery. And because of this, now the charges will start flowing. This first plate will accumulate positive charges, and this will accumulate negative charges, and the charges will now flow through the resistance R. And as the charge accumulation starts, as the charge starts building up on the plates of the capacitor, an electric field will set up. After some time, when voltage across the capacitor between plate 1 and 2 is same as that of battery, the flow of charges from positive terminal of the battery to positive plate of the capacitor and negative terminal of the battery to negative plate of the capacitor will stop, and we will have a situation, or we have a situation where we have the equilibrium, because there are two potentials, one due to battery and one which is developed in the capacitor. Across the plates of the capacitor, they are opposing each other, so no current flows, and that basically is how a capacitor charges. Now coming at the displacement current. To find the displacement current, let's imagine that this electric field is suppose E at any instance of time. Suppose electric field between the two plates is given by E as a function of time. And now I can use Gauss's law here. I will use Gauss's law in order to explain what displacement current is briefly. What is Gauss's law of electrostatics? It you can tell me the equation. Not Gauss's law of divergence, but Gauss's law of electrostatics.
Integration E into ds is equal to enclosed charge upon epsilon naught.
Is this right? This E is the electric field, and integration is over the closed surface, and ds is the surface element over which we are integrating it. So if we use this equation, and we have another word here, which is current. So we have to use this also. So how do I find the current? Current basically is when I differentiate Q with respect to T, or how much charge per unit time is passing through particular point in the circuit is current. Now in this case, the current or the displacement current is due to this electric field. Since the electric field is increasing, it is going to change with time. And with Gauss's law, you can see that there is relation between Q enclosed and the electric field. So as Q increases, electric field goes on increasing, and this increasing electric field is actually responsible for the displacement current. So what we can do is we can consider a small section here, or small surface here, which is closed surface. You can imagine it like a box. There are two walls of the box which are parallel. This wall and this wall. These are the walls which are parallel to the plates, and it is enclosing the plate number 1. And then you have bottom, the uh, the ceiling, and so this is the bottom of this box, this is the ceiling or the top of the box, and then there are two surfaces which are parallel to the screen, which I cannot draw here. They are oriented something like this, parallel to the screen. So this is the box. And now if I use Gauss's law for this case, electric field is perpendicular only to these two walls which are parallel to the plates. The other four surfaces, they are perpendicular to electric field, and therefore the dot product is 0. In this case, this surface, normal of this surface and electric field since are parallel, the dot product exists only for these two. But at the same time, for this surface, which is outside the electric field is zero, and therefore it does not contribute to this integration. And we just have to consider this surface. And Gauss's law, therefore, out of 6 surfaces, only one surface gives the contribution to this integration, which is E into dA. For parallel plate capacitor, if we ignore the boundaries, which is true, which is practically correct most of the cases, because when we consider macroscopic large capacitors, electric field is constant, and therefore I can take it outside integration, and this simply becomes A, where A now is area of cross section of the plates, and this is equal to Q enclosed. So if I differentiate this partially with respect to T now, what I get is epsilon 0 dou E by dou T into A is equal to dQ by dt, where this in this case the charge is not actually flowing, but it is being accumulated with respect to time on each of the plates. One is accumulating positive Q charge, the other is accumulating negative Q charge. Now this dQ by dt is the displacement current. Okay, so this is what displacement current is briefly. Though we don't need this equation directly in this case, I explained it because it is possible that some of you might not have yet studied what displacement current is. I hope that you have at least partially idea of what displacement current is. But to solve, now let's try to solve the problem actually. We have to now solve the problem. What we want to find out is this term dq by dt. Figuring this out is definitely difficult. So what I'm saying is the displacement current is the right hand side of this equation. So this is the displacement current term. If you knew the left hand side here, we could have calculated that, but it is now difficult because we are not given any dimensions or details of the geometry of the capacitor. So we have to definitely take a different way. And that becomes our key concept for solving this problem. I explained this just to explain to introduce what displacement current is if you already didn't know that. So what is the key concept here? If anyone wants to try, which we need to solve the problem. Does does anyone recall the equation for charge developed as a function of time on the plates of the capacitor?
Q नोट ब्रैकेट के अंदर 1 माइनस e to the power something I forgot.
Something is minus t, right? That is right. Minus t by RC.
Yes.
This t is time, and RC, if you do some work here, or if you go back and have a look, let me draw this square
Time
bracket around
constant.
I. Pardon? Okay. So this, is there anything? No. This square bracket around RC is basically I have drawn to denote that I am now considering the dimensions of RC. So dimensions of RC, this product, current and capacitance, have the same as that of time. And that is called for RC circuit as the
Time
time
constant.
constant of the circuit. Yes, right. Thank you. So we have Q, and we want to find out the displacement current. So what I do, I differentiate this with respect to time. Though the maths is simple, it says differently. You should be very clear here that Q is not flowing with respect to time when it comes to the plates of the capacitor. We don't have a closed circuit, it's an open circuit. This is accumulation of charge per unit time on the plates. So if I differentiate this,
dt0 upon dt.
Yeah, so we differentiate it. This Q0, let me keep it as it is. Differentiation of 1 with respect to time is 0, minus, now I have to use the chain rule. Differentiation of e to the power exponential is same. And then I have to multiply it by differentiation of t T by RC, which is minus 1 by RC. Therefore, this turns out to be equal to Q0 e to the power minus T by RC into RC. Okay. Now, what is Q0 in here? Q0 is the maximum charge that capacitor accumulates when it is connected to a battery of voltage V. And that CQ0 is product of C into V, where C is the capacitance of the capacitor and V is the voltage of the battery that we have connected. Therefore, this will become C into V divided by RC into e to the power T by RC. So this CC cancels and we have equation for displacement current. ID is equal to V by R into e to the power minus T by RC. Now, if you look at the right hand side of this equation, V is given to us, which is 6 volt. R is known, which is 10 kilo ohms. T is time at which we want to find out. So V is equal to 6 volt. R is 10 kilo ohms. T is 500 milliseconds because at that particular instance, we have to figure out what the displacement current is. And C is how much? 600 microfarad, if I'm not wrong. How much is it? It's 600 microfarad, right? No, 100 microfarad.
100 micro.
Yeah. So you then plug in all the values. All the quantities on right hand side are now known. So we can plug in the equations. Now it's little bit difficult if you try to do it algebraically, but I think you are allowed to use the scientific calculator in the examination. So I'll simply, you can plug everything in there in the calculator and you can verify later that this ID turns out to be equal to 364 microamperes or 364 into 10 to the power minus 6 amperes. Is it okay? So this turns out to be the answer, which is one of the options in the examination if you see the question paper. Is it clear? Any doubts in this problem? If
No,
no,
sir.
then perhaps you should tell me what are the key concepts that we need to solve the problem first, without which solving the problem wasn't difficult. What is it? Okay, let me explain why I'm doing this. If you start doing this practice, in my experience, what happens is as you practice more and more, you automatically start thinking or try to figure out what are the concepts that you need. And once you have that, though you do it subconsciously, you try to figure out what are the concepts. It becomes easier to solve the problem instead of wondering uh, about thinking of the different topics and different equations. If you train yourself to identify the key concepts, it becomes easier for solving a problem. That is what I have experienced this far. That's why I'm having this particular practice or this particular exercise. What is the key? What are the key concepts? Single is fine, but should not be more
Displacement
than. Yes.
current, displacement current itself, and
Yeah,
equation
the
of charge,
concept of displacement current you should know, of course.
and the equation of charge.
Yes, if you know the equation of charging of capacitor, right? Q T for charging. And what are the skills that you require?
Differentiation.
Differentiation, yes. And I think that's all, right? Second key concept that you need to know is Q0, the maximum charge, which is C into V. and then basic algebra. That's all. Am I right? Am I missing anything in skills or the concepts that we need to solve the problem? Shall we go to the next third problem number 3?
Yes, sir.
Yeah. Okay, so let me switch the screen. Let's read the problem first. So this is third problem. If the charge density, which is denoted by rho, in a poorly conducting dielectric medium of conductivity sigma and permittivity epsilon is rho 0. So what we know is there is some region of space where the charge density is given by rho, and at time t is equal to 0, the charge density is rho 0. We know that this charge is placed in dielectric medium, which is not a good conductor, and it has conductivity which is sigma, which is denoted by sigma. So what we want to find is the next sentence says at later time t, this should be correct. This is not correct. At later time t, the charge density rho is expressed as. So this equal to 0 in the second sentence should not be there. So let me again write it down here. So what we are given is rho 0 is initial charge density. Rho of RT is charge density at a particular point after at time instance t, and rho 0 is charge density at t is equal to 0. We know that conductivity is sigma, and we know that the permittivity of the space is given by epsilon. And we want to now find out equation for rho RT. So where do I start? Let's start. Let me draw a diagram, or rather a figure, a sketch rather. So we have this region. Let me consider a small region out of that. And now, since charge is concentrated here initially, suppose in this small region, what will happen is, though it is dielectric medium, it doesn't have infinite resistivity, or its conductivity is not zero. It is non-zero. So some charge will start flowing, though very slowly. Charge will start moving out, and because of this, the charge density, which is initially rho 0, at time t is equal to 0, will go on decreasing. That we know for sure, that the charge density outside the region where the charge is non-zero, the charge density as a function of time will go on decreasing, and we want to find out that relation. So where do I start in this case? Which equation? Any concept that comes to your mind? uh okay, how many of you, please raise your hand if you are familiar with equation of continuity for charges, for electrostatics, electricity. How many okay, how many of you have not yet come across the continuity equation in electricity? Okay, let me quickly explain that. Okay, so let's consider this simple situation which this sketch is trying to draw. What we have is charges here. At t is equal to 0, the charge density is rho 0. Now, since the conductivity is not 0, it is non-zero, the charges will, with time, start moving outside the region of this region, which is, say, placed at R, and it is very small region. So its volume is dV, which is infinitesimally small. So if I want to now write by how much the charge changes with respect to time, I have to differentiate it with respect to time. dq by dt is what I have to calculate. Again, this is not I mean, this is basic. What this dq by dt is basically the current which is flowing outside the region, and that is responsible for taking the charge from this concentrated charge region to the surrounding. And now what we need is rho here, which is charge density. What I have is charge itself. What is relation between q and rho? Suppose in the beginning I imagine that rho is uniform. It is not function of space. So what should be the relation between charge and charge density?
So Q by volume.
Rho into q by v is
Volume.
rho, right? Yeah.
No, I said Q by V equal rho density.
Is this what you are saying?
Yes, sir.
Yeah. So let me rearrange this and write it as q is equal to rho into v. How does this change if I consider rho is not uniform? I just
Uh,
have the integration now, right?
yes, sir.
So let's plug that in this equation. So what I have is differentiation. I will write partial differentiation because rho now is function of both space and time. So I have to consider partial differentiation of q, which is rho integration rho dv, and this is equal to I, which is the current, which is basically charge per unit time moving outside. Now you must be familiar with J, which is current density. If I have a plain cylindrical cross section wire through which current is flowing, then J is basically I by A, which is current per unit area. That's why it is called as the charge density. So I have to write in terms of J, because to obtain the relation. So therefore this J, again, since or in case where the current is uniform, you can simply write it as uh, you can write I as product of J into A. But when current is not uniform, which is the case, which is a possible case in our scenario, we have to write it as integration J dA. And now what we have is this relation between rho and J. Okay, so we uh, now somehow I have to obtain an equation so that this area integration can be written in terms of volume integration. And how do I do it? This right hand side, which is area integration, now I want to write it as volume integration. Why? Because on left hand side I have the volume integration. So which law, which concept do I use here?
Again, Gauss divergence theorem.
Gauss's divergence theorem. Yes, thank you. This is basically, it says Gauss's divergence theorem says that this can be calculated by taking divergence of J and then integrating it with respect to volume. And therefore, what we have now is rho dV on left hand side, which is unchanged. But by using Gauss's law, instead of J dot dA integration, I will write this integration. Del dot J dV, both of them are now integrated. Left hand side and right hand side are integrated over volume. And therefore, I can separate it and I can write it something like this. I just have got rid of the integration because anyway both the terms are integrated over the same volume. Now there is a small correction. Can anyone uh, can guess what is the correction in this equation that I have obtained? From the arguments that we have been following, what should be the correction here? I'll give you a hint. What we are talking about, this density is basically density of this region, where because of the small conductivity, the charges are being taken out, right? So current is moving outside and that is positive. So what is the correction here? What will happen to charge density with time? Does it increase or it decrease?
It should be
Reduce.
negative sign, I think.
Right, it is negative. So rho by dou t is negative. So we have a negative sign here, and the equation then is with a negative sign. Or this equation many times, in many textbooks, many references, you will see that the equation is written something like this. And this is called as equation of continuity, which basically tells you that charge leaving out should be related with current density in this particular way because charge is conserved. So this is equation of continuity. Is it fine? Next step now we need, so the first key concept that we need to solve this problem is this equation of continuity. The next equation that we need is this is for this j. How much time, sir? How much time is left?
So you can take 5 minutes more because there is another meeting on the same link by Central IAPT.
Okay, okay, sir. So,
I just got the message from the General Secretary. They are going
okay,
to continue the same link for the other session, please.
okay, fine, sir. I'll rush through this particular problem. So the first concept that we used is this equation of continuity. Second, now you use uh, this relation for J, where you can write J as rho into E, where J is the current density, E is the electric field, and sigma is the conductivity of the medium. This is basically Ohm's law. If you consider Ohm's law, which is generally written as I is equal to V by R. So yeah, and differentiate it, do some mathematics, you come up with this equation. So therefore, this equation then can be written as d rho by dt plus the sigma is a constant. So sigma can be written outside for the second term in equation of continuity. And then this is del dot j equal to 0. So this is another way you can write the equation. And now if I rearrange this, dou rho by dou t is equal to minus of sigma into del dot v. And v from Gauss's law, oh sorry, not v, electric field. From Gauss's law, we know that del dot E is charge density divided by epsilon 0. So therefore, dou rho by dou t turns out to be equal to minus of sigma, which is conductivity, and del dot E is rho, which is charge density divided by epsilon. And we have the differential equation now, which we can solve to figure out rho as a function of time at that particular space. And this equation is, when you integrate it, it becomes rho 0 into e to the power minus t into sigma by epsilon 0. So this gives us, or this is the answer to the third problem. So quickly, how many or which key concept do we need here?
Sir, what you did in last step?
This one?
Yes, sir.
Yeah, see, what we want to find out is how rho is changing with respect to time, right? So I have obtained this differential equation, which gives me a relation for how the density is changing. So you have to
Oh,
integrate
okay.
it.
You
So you
solve
just have to
differential
integrate it.
equation.
Yeah. Solution of this differential equation is basically this one.
Okay.
Okay. And that is the relation that we want. Okay. So what are the key concepts here? First,
This equation of continuity.
continuity equation of continuity.
And
Second, Ohm's
this
law,
goes driver. Yes, sir.
because here we used Ohm's law to write current density in terms of electric field.
Mm.
And finally, the third step or third concept that we needed was Gauss's law of electrostatics. right? With these
Yes,
three
sir.
concepts, and with, of course, the skills which are uh, some basic algebra and then solution of the differential equation, we can arrive at the solution of this problem. Is it okay? Any questions? Are there any doubts?
No, sir.
If no, then I think we will stop. I will stop sharing the screen. Sir,
Yes, any question? If
No,
you have any
sir.
question, please raise your hand.
uh, just a comment, sir. Last comment.
Yes, sir.
Uh, uh, Please share my email ID and even phone number is fine with
Sure.
them, because we were not able to solve all the problems from the problem set. If they
No
have
problem,
any
sir.
questions in any of these problems, or in general, it's okay if they contact me. I would be
In
happy
that
to
case,
help.
can you please possible, if it is possible, can you share the solutions of the problems which you have taken the today's session? The today's
The
test,
file
the
itself
strict.
I can share as it is, but for writing it neatly, it will take some time because I
No
haven't
problem.
written it. So,
No problem.
but when is the exam?
Exam is on 25th, the coming Sunday.
Oh, uh, okay. Let me see if I could write the solutions neatly and then share with you. Otherwise, whatever work I have done today, I will share it immediately.
Sure, sir. Sure. No
Yeah.
problem. Yeah.
Okay. That's
Okay.
all then. Over to you, sir.
So, yes, sir. So let's come to the end of the session. So on behalf of Pune, IAPT Pune SRC and Central IAPT, also on behalf of our General Secretary, Professor Rekha Ghurpade ma'am, and President Manisha Hawaldar ma'am. So we are thanking you, sir, for your time and for delivering the today's session. Today's session was very interactive, and I'm happy that students have also participated in today's session very actively. So thank you very much for your time, sir, and I thank all the participants. Now we end this session at this note. Thank you so much. So tomorrow we'll be having a session on electronics and statistical mechanics by Professor Kati, sir. So I officially conclude this session. Thank you so much.
Pleasure to be here, sir. Thank you
Yes, sir.
for
Thank you.
inviting.